Okay, welcome everybody to this webinar. We have a great session planned for you today with our three speakers from three companies all working together to accelerate photonic IC design. So I will start with introductions to our speakers today, and then I will move on to a quick overview of the schedule for today, and then some instructions on questions. So first, I'll start by introducing our speakers. So from ANT, Applied Nanotools, we have Cameron Horvath, who's the Director of Integrated Photonics, Applied Nanotools, which is headquartered in Edmonton, Canada. He oversees all operations for the NanoSOI rapid prototyping Foundry service and regularly performs R&D and other fabrication work for custom and multi-project wafer fabrication runs. And he has 15 years of industrial experience with micro and nano fabrication, photonics, and software development. So welcome to Cameron. And then from Alcyon Photonics, we have Thibaut Bourguignon. Thibaut is a PIC design engineer at Alcyon Photonics. He's leading the Photonic subsystems team and is responsible for the development of Alcyon's libraries inside Luceda PICs. And he has 5 years of experience within the semiconductor industry, including a PhD in high volume manufacturing Foundry. And lastly, I'll introduce myself. My name is Craig Godbold. I'm an application engineer at Luceda Photonics. My main role is in business development, but I also do training and support for customers. I have a background in photonics. I studied here in Belgium, where Luceda is based. I also spent some time in another industry, in telecom, before circling back to work in integrated photonics. So it's nice to welcome you all today. And I'll give you a quick overview of the session. So we'll begin with Luceda. So I will be talking about how our platform can seamlessly integrate with Alcyon's PIP cores, IP library, and supporting the entire design flow from simulation to verification. And then Cameron will talk about the NanoSOI rapid prototyping Foundry service for silicon PICs and highlighting the MPW fabrication options like oxide cladding, thermal optic phase shifters, and edge couplers, the fast turnaround that they offer, and the high resolution patterning using 100 keV electron beam lithography. And that Foundry PDK is also available on Luceda's platform. And Thibaut will finally talk about the comprehensive IP library for ANT's NanoSOI, featuring key photonic integrated circuit or PIC components, and how they are accelerating design using these advanced library components. And so by the end of this session, you'll understand how this black box IP that Alcyon has developed, leveraging ANT's rapid prototyping service, can accelerate PIC development and simulation to fabrication with ANT. Let me give you a quick overview of the timeline. So we'll begin by giving you an overview of Luceda Photonics and how you can use this advanced photonic IP. And then we'll pass the floor over to Cameron from Applied Nanotools to talk about their rapid prototyping Foundry service. And we'll finish with Thibaut explaining Alcyon's PIP cores. And we'll save questions for the end. So we have 10 to 15 minutes for questions. I would ask you just to hold off on questions. You can type them into the chat so we can pick them up at the end. And you'll have an opportunity to turn on your microphones and ask questions in real time. Okay, so let's get going. So I'll begin with an overview of Luceda Photonics. So Luceda Photonics, who are we? So we're a Belgian company born out of the photonics strong research ecosystem here from the universities of Ghent, VUB, and IMEC. And so we're now just over 10 years old, so we're into our 11th year. And the vision of Luceda is to help photonic IC designers enjoy the same first-time right experience as electronic IC designers. Our mission as a company is to help accelerate the time to market, which is crucial when trying to bring products to the market. As you can see from the map, we're now a global company. We have a global presence and have done for some time. We have an office in China, our official partners in the United States, Spark Photonics, as well as resellers in Japan and in Taiwan. And crucially, we're a team of photonics experts. That's our speciality. Now, I mentioned the vision of the company, which is the first time right experience. So how do we do this? Well, we have the Luceda Photonics design platform, IPCIS. And we're predominantly a code-driven flow. And where you see from this image where you can follow the full design cycle from component design to circuit design. You can do validation and simulation, and in the end, produce a GDS file for manufacturing. So to get this first time right, the idea is to reduce design errors. So how do we do this? Well, working in code, working from a single source of truth. So we leverage a standard language, which is Python, which our API is built on top of. And this helps give fine granular control over your designs. And the power of this is parametric design principles. We also need to make sure the PICs, the PICs, are manufacturable. And so we do this with the quality of our design platform, but also access to Foundry PDKs and library IP. And this empowers designers to use validated components. And all this together improves the time to market. So an overview of Luceda Photonics. So in the center here, you see Luceda IPCIS. So this is the central platform that brings everything together. This is where you will do your work. And this is where you can do your component design and circuit design. So we have lots of functions for easy design and layout. We can do optical and electrical routing. We have some capabilities for electromagnetic simulations with EME, but we tend to link with third-party tools that are well known in the industry for physical device simulation. You can do circuit simulation. We have a powerful circuit simulator called Café. We have a schematic capture tool that enables you to do a schematic-driven approach to design, as well as design validation. And all of this, in the end, leads to producing your GDS file, which you will use for fabrication. You see on the left-hand side the design kits that are available in the platform. We work with all different foundries across different material platforms, as well as having design kits for assembly and testing, so going even beyond the fabrication. In addition to IPCIS, we have a few other products, which I should mention. So beside the flagship product of IPCIS, we also have an AWG designer tool. So this is a special tool for accelerating the process of designing an AWG. We also have tools for IP management and quality control. And as well as a new tool we've just released, which is called Luceda Circuit Analyzer, which enables advanced circuit level simulations and variability analysis and so on. I'll just walk you through a couple of the steps that you can follow when going from idea to tape out. So you can start with component design. You can design your own components in IPCIS. So again, we're leveraging Python as the language. We can easily build these layouts and define models for them if we have the simulation results, or we can use analytical models to do this. We can then do a virtual fabrication of the component. This can then be exported to third-party simulation tools, as well as using our own internal EME tool. IPCIS is very well suited to the circuit level of design, so we can take components that we have designed ourselves, or building blocks and IP that we have imported, and we can build complex circuits with ease. So we use the power of parametric design principles, and we can use many of the smart optical and electrical functionality that exists in IPCIS to construct circuits such as these you see here. We can do complex bundle routing, we can do obstacle avoidance, we can do multi-layer metal routing as well. I mentioned circuit simulation, so this is perfectly possible in IPCIS. If you have components that have models associated with them, you can certainly simulate the performance of the entire circuit. And something very nice with IPCIS, there's a tight link between the layout and the simulation. We have the circuit designs that are well parameterized, and so you can vary a parameter, get a new layout, and simulate that layout. You can do circuit simulations in both frequency and time domain also. The standard way of working is to use code, but we can also use our schematic capture tool, IPCIS Canvas, to start designs. So this is one approach to design where we can do a schematic capture with code assistance. We can take PDK building blocks, library IP, and we can drag and drop that onto our schematic tool. And from there, we can generate the Python code that corresponds to that circuit, which can then easily be optimized. It's also a powerful tool for communication. So working as a team, you can easily export your designs to the schematic tool, and it's a great way to communicate around a design in a team. In addition to that, you can also do design validation using Canvas. So this enables you to verify the connectivity of your circuit to make sure your layout is correct. You can do both optical and electrical netlist extraction, as well as post-layout simulations using our circuit simulator from within the Canvas environment. Another nice feature is you can also 3D export your designs to be imported into other software tools. Another important aspect of photonic design where we can really help you is with tape-out preparation. So it's very important that your design adheres to the rules from the Foundry. So we want to make sure that there are no DRC errors. And so we have some nice functionality in the software that will help you address the most common DRC errors. One example here would be acute angles. These can appear in your design very easily without you noticing. And so we have some smart functions that enable you to identify and patch all of those very efficiently. Design kits I mentioned. So we work with all of the material platforms, and we see that today in this session. An area where we excel is in training support. This is something that can really add value to you if you're working with our tools. We offer a lot of training to help you get started with the software. But we offer a lot of continuation training. We have a customer support portal, which is very active. So whenever you have questions, we're there to help. Our online training documentation is extensive, and all of that comes shipped with the software. And so we recommend after this, you can check out the Luceda Academy, and you will find many interesting application examples which highlight the power of the software. And here are some of the examples you will find if you look through our academy, but of course you can reach out to us if you have questions or want to know more. So we work with more than just foundries, so we're well known for our relationships with foundries, but we also have many collaborations. We're a true ecosystem player. So we work with other softwares, design services, we have other photonic IP providers, as well as just many other ecosystem partners. And finally, and this sort of captures what we will see today, is this sort of relationship that we have and how we work together. And so here we see Luceda. We're here to empower designers with first-time right designs, but to do that, we rely on the people we work with, our partners, the people we collaborate with. And so here today we have Alcyon, who have built their amazing IP cores on top of the technology from Applied Nanotools. And as you see here, these are how these relationships work. We all work together to push PIC design forward. And so with that, I'm going to hand over the floor to Cameron Horvath from Applied Nanotools, who will take you forward for the next parts of the story.
All right. Thanks, Craig, for the introduction. And welcome everyone to our joint seminar, webinar, I should say. I'm pleased to introduce the NanoSOI fabrication service for rapid prototyping of PICs in silicon and silicon nitride, although we'll be focusing more on silicon today. Yeah, so here's sort of a general overview of our process. So really it is a rapid prototyping service that can produce PICs on a timeline as short as 3 weeks. Now we have process options that we can add on top of that flow. So it can be as short as 3 weeks or, you know, as long as 2 months or even longer if you're doing dedicated runs and need different capabilities on top. So the crux of our process is that we can pattern features down to a 60 nanometer critical feature size for silicon using 100 keV electron beam lithography technology. So what this does is actually enables the fabrication of sub-wavelength components. And these sub-wavelength components are very powerful because it removes the need in a lot of cases to do a partial etch of your PICs. And adding these partial etch steps into the process flow can be quite time consuming and costly. And so what this allows us to do is produce things fast and with less expense. Also, Alcyon Photonics has designed a whole wide array of components that leverage this sub-wavelength engineering property of our fabrication service. So Thibaut will introduce those components in his session. So as I mentioned, the turnaround time for our service is as short as 3 weeks. Now, adding these process options does add a bit more time, but you may be pleased to know that we offer not only the waveguides, but we offer thermo-optic phase shifters, edge couplers for edge coupling, which adds a bit more time. We also, in some cases, can add partial etch to your project as well. Feel free to reach out to us directly if you do have any partial etch requirements. Our losses are kind of shown on the right here for our SOI process. So straight waveguides, you know, we're sort of at the, call it industry standard sort of level of propagation loss. Curve waveguides are a bit higher just because of discretization losses with E-beam. E-beam tends to not be able to pattern bends as nicely as it does straight waveguides, so there's a bit of a penalty there, but the technology keeps improving over time. 220 is sort of the standard MPW option that we offer, although we also offer 300 and 500 nanometer SOI in dedicated runs. And then as you can see by this flow chart here, we offer a whole array of different options that you can add to your project. And these are optional, so you don't need to add these if you don't need them. So you can choose to add either oxide or air cladding to your project. And then if you add oxide cladding, it sort of enables a whole bunch of other things that you can do, like add heaters. You can add isolation trenches to thermally isolate waveguides from one another. You can do oxide window openings, edge couplers, as I mentioned. So I'll dive a bit deeper into each of these sort of modules here, just to give you an idea of what's possible. So with the tri-layer metallization process option, you can implement these phase shifters on chip. So you can thermally control the optical properties of your waveguide with microheaters. So we feature titanium tungsten microheaters with gold traces. Used to be aluminum, as you see here, but we moved to gold just because of better wire bonding, yield, reliability, that sort of thing. So we're always improving the process based on feedback. If you want to isolate, two heaters, two waveguides from one another thermally, you can add these trenches internally to your design. So in this example here, we've got a couple arms of a Mach-Zehnder interferometer type structure that we need to sort of thermally isolate from one another. And so you can place a trench in the middle and it mitigates thermal crosstalk. And there's some diagrams down here to kind of show how that works. In dedicated runs, we also have a sort of a different flavor of this process where we can actually laterally etch horizontally through the silicon as well. So you can actually, with two trenches, you can fully suspend a slab of oxide, silicon oxide, and that can really get you some enhancement in your thermal switching efficiencies. But that is a dedicated run option, so not available in PW runs. And then I mentioned we do have a full edge coupling process. So this involves etching trenches along the perimeter of the dies, and then doing a smooth reactive ion etch process to give you facets. There are some polishing post-processing options available on the market if you do want a full etched facet without this ledge present. And in some cases, we can even do this RIE etch all the way through the wafer as well. So it avoids the need for polishing completely. Oxide window openings are another option where after depositing the oxide cladding, you can open up windows in the oxide and you can reveal the waveguide to the ambient environment. So if you're doing sensing or if you're doing some specialty component development, you may want to get rid of that oxide on top. And in dedicated runs, we can even go a step further and do a full release. So in this image down here, these silicon beams are actually suspended because we did a two-step process where we opened up oxide to reveal the waveguides, and we had another process where we go a bit deeper and actually eat away the SiO2 from underneath the silicon waveguide, causing it to be suspended. Now this is very dependent on the mechanical properties of your structure, so your mileage may vary here, but it is an option. Yeah, we talked about losses already. These are just some sort of random fits that we did on a wafer a couple months ago, just showing sort of what typical propagation losses we see with our process. Nitride, I know I wouldn't talk much about nitride, but we do have a nitride process as well. We're looking at sub dB per centimeter losses for nitride as well. And this is a newer platform for us, so these specifications are always improving. We're also planning to release a 150 nanometer thick nitride platform in the near future. So stay tuned for that. A lot of people don't realize we're also involved in automated circuit measurements. So for some select projects in the C-band that use vertical grating couplers, we can perform automated circuit measurements. So it involves, producing a net list, mapping it to coordinates on your IO on your chip, and measuring circuits sort of in an automated fashion. So if this is of interest, please reach out to us. Be happy to guide you through how to design your chip for test. These are some SEM images of some components that you can make with our service, and not only components of systems, of course, using these components, but this just gives you an idea of sort of the power of the resolution, subwavelength patterning capability that we have. So these structures here on the right are using sub-wavelength components, which removes the need for us to do partial etching. So this grating coupler lets you couple light from an incident angle of 8 degrees and couples it into your chip, and vice versa, lets you emit the light back out at an 8-degree incident angle. We have a version of an edge coupler called a sub-wavelength nanotaper. So this sort of equalizes the polarization dependent loss between TE and TM polarization, in case that is a metric that you want to optimize. We have the normal flavor of nanotaper as well, which just serves to try to reduce insertion losses to an absolute minimum. So that's also an option. These components are available in the Luceda PDK, which I will dive into toward the end of my presentation here. As I mentioned, multiple etch steps are possible. Come talk to us. Everyone's got a different requirement. We're open to depths. We're open to the order in which we do things. And these etch steps are sort of a prerequisite in a lot of cases to doing active devices. So in dedicated runs, we will also entertain requests for any devices requiring ion implantation. So we do have an implant service provider that we work with, and have some canned processes that we've developed to implement things like high dopant concentration junctions, contacts, PN junctions, and that sort of thing. This is an example of a, we call it an ERF device. So it's sort of a combination heater, photodetector sort of device. If you want to learn more about it, we linked a publication here that you can follow and learn more about. We have some packaging solutions. So in-house, we have sort of a project PCB option that you can get us to glue your PIC to. We can do the wire bonds in-house, and it comes with a ribbon cable that you can connect to these power supplies sold by a company called Control, or you can use your own programmable power supply if you like. It's a 50-pin ribbon cable that this thing connects to. Integrated thermistor for temperature control as well. We also work with PICs as sort of a third-party packaging provider if there's even more advanced packaging requirements than this. So feel free to reach out to us there. Yeah, I just wanted to highlight, we have MPW and dedicated runs. The MPW runs do run on a schedule, and they're actually offered fairly often. So this is sort of the schedule that we're looking at for 2025. You can see that we offer the runs roughly every 2 months. So there's 6, maybe even some cases 7 runs per year for SOI. So there's plenty of opportunity to submit a design to us. And all of the design submission is done through this NanoSOI Design Center, which I will just briefly give you an overview of here. So yeah, if you, just to get here, you visit our main page, you go to Integrated Photonics, you choose Design Center, and here you are. So it gives you some news about the process, any changes that we've introduced. If you go into Silicon Resources, you can see all our design rules. You can see overview of the various process options that we offer. MPW run schedule, as I just shown you, is here. And then we can dive deeper into each of the process modules and sort of some examples that we have for them. So tri-layer metallization has like a neat little tutorial here on how to make a phase shifter. Edge couplers, we got some data here showing insertion losses, thermal isolation trenches. Again, we got some examples here. SEM imaging, I just want to mention, we also offer sort of an in-situ SEM imaging option with our fabrication service, where you can ask us to take SEM images of your waveguides before the fabrication has been completed. Because it's often hard to take images of your structures after you've put oxide cladding on top of them, and you ruin the ability to do precise scanning electron microscope imaging of your stuff. So you can place these layer 200 boxes on your GDS files and request images from us that way. Custom dicing as well as an option. So if you purchase an MPW slot from us, you're not necessarily restricted to just one chip. You can get it subdivided into 2, 4, even 9 dies if you want. If you need more than 9 dies, and you just purchase more MPW slots from us. So that's sort of how the allocation works for every wafer run. And then packaging and measurements, these are sort of being built out at the moment, but we can maybe go to our PDK here and talk a little bit more about how to get started here. So on this PDK page, you can find the Luceda PDK here. There's sort of a 2-step process for requesting the PDK. So if I go down to my, hold on a sec here. This slide here, there's a request step where you need to first ask us for the PDK. Now, this does not require an NDA. All it requires is for you to fill out a questionnaire, just giving us some information about what you plan to use the PDK for, how we can improve it, what you'd like to see out of it, that sort of thing. Once the approval is granted, usually it takes a day or two. You can download the PDK from the same page, and there's an installation guide and everything available there. So if you go into the PDK documentation, you'll see that there's some descriptions about each of the components here. These are the vertical grating couplers that I mentioned to you earlier. There's an air and an oxide variant of these. So depending on your cladding material, you got to choose the right one. We got some splitters. We got a ring resonator we've optimized over several runs. And we've got some edge couplers here as well. So really it's the foundational IO components that you need to get started with our process. And then Thibaut from Alcyon is going to talk about their components that are sort of an add-on to ours. So it will add much more functionality to your photonic circuits by leveraging Alcyon's blocks as part of your project. And then lastly, the submission center also is where you submit designs. So there's this page you fill out and you can submit a design. But don't know if I have enough time to get through the submission process. And if the Q&A is quiet, I can maybe show you that. But we'll leave it at that. And let me know if you have any questions in the chat or at the Q&A session at the end. With that, I will pass it on to Thibaut at Alcyon Photonics, so we'll talk more about those specialty building blocks that I briefly mentioned. Thanks.
Thanks, Cameron, for the presentation. Let me share my slides. And if you can confirm that you see them, and that you can hear me well.
Yep, we can see your slides and can hear you well. Perfect.
So hi, I'm Thibaut. Thanks for the opportunity to present to you how you can boost your PIC performances and reliability with Alcyon's PIC cores inside Luceda PICs. So Alcyon, we are a small company based in Madrid in Spain, and we aim to support the PIC development all around the world with high performance and Foundry validated designs. So what we do is we usually do IP designs on top of existing PDKs. So today we'll present to you what we did for ANT. So we aim to be complementary with the foundries. So as Cameron showed, they have already all the I/O devices, and we on top of this we will add some couplers, some polarization devices, etc. But we also provide some custom design services to our customers, so we can accompany them from the design phase up to the tape out with them. So including DRC and all these very complex steps. We have some high performance blocks that I will go into detail with you today. So here are an example of the one you can find in ANT Foundry. We've mostly focused on low loss, very broadband devices, and with a low phase error. We also try to have a very consistent response, so all the blocks we provide are very competitive over all the foundries we work with. This is, for example, a device we designed with Applied Nanotools. So it's a broadband directional coupler that is actually using these subwavelengths grating that Cameron mentioned before, which is very broadband over the whole C plus L plus U band with a very good coupling ratio, which wouldn't be possible with conventional designs. And as you can see here, we even proved that we could apply what we learned with INT to deep UV foundries, and with in yellow here, our coupler already performing well on the first tape out with them. We will improve it again in another round, but it's already very promising and good. We also focus our designs and IP into robustness. As we know that DUV processes have a lot of variation, we try to prevent this to affect the performance of our blocks. So what you can see here is a result we published couple of weeks ago in a white paper you can access on our website of a fabrication tolerant demultiplexer. So we fabricated this multiplexer 2 on a full wafer. We have 15 chips measured here. And as you can see, the Alcyon approach offers a very stable signature. And we have only 0.3 nanometer of spectral shift over the whole wafer, thanks to our own custom design. For the Mach-Zehnder interferometer, we even showed 11 piconanometer per picometer, per nanometer variation with the width, which is around 20 times smaller than a classic MZI. This is feasible thanks to our great partners, so Luceda and ANT today. And I will now shift into our library for NanoSOI 220. So what we bring today is 9 components that are ready to be taped out for every of your designs in the C band. Among them, there are MMIs 1x2, 2x2. We have some different versions of each MMI depending on what is your priority, if it's a feature size, if it's length of the device, or to be more broadband. We have more demultiplexing devices, polarization beam splitters, and directional couplers, along with the crossing. What we always focus is on in this library is the broadband. Most of them are C plus L and U band. Our MMIs are very low phase error compared to classic MMIs. And all these devices has been already fabricated, characterized, and we even push further with corner analysis and some Monte Carlo simulations. So you can use them confidently in your design and process bigger PICs thanks to our IP. All these compact models, especially for the TE, are already available in the PICs library, so you can already simulate as soon as you have it. I would like to go into details to a couple of our devices that I really like. We have this MMI 2x2 version 2, which has quite impressive performances with only 30 micrometer long compared to classic MMIs. It's quite short. And we showed a very broadband device, and here you can see the phase error is very small over the all C plus L U band again, with the straighter lines being what we simulated, and the more curvy lines what has been measured in a couple of chips fabricated. We also offer a polarization beam splitter that aims to separate the TE from the TM mode at the output, and an adiabatic directional coupler that is functioning both for AT and TM. A last one, which is our broadband DC coupler for TE mode, and this one also leverages the small feature size possibility of ANT, and it shows a very broadband signature S matrix over the whole C plus L U band again. As a comparison, I showed here in orange a conventional coupler model based on the classic mode theory, and you can see it has nothing to do. We managed to stay around -3 dB over the old bands. We proved it's robust with ANT's process. Here on the right, you can see the simulated behavior of our device, and in dashed lines, 2 chips that have been measured out there, fabricated and measured. This is a directional coupler, which means that here is designed for 50-50 coupling ratios, but we can always offer any coupling ratio you want. So feel free to ask. Our goal was to be able to deliver to our customers this IP, but by keeping the privacy to protect both our IP and the one of the clients. So what we developed, thanks to Luceda and ANT, is a black box system. So only ANT is going to have the open IP version of our designs, and the customer is going to have the black box one. So as you can see here, just contain the outline and the port. All the port information is contained inside the software of PICs, so the user doesn't have to think much about the mode, the width, and the orientation of the port. It's all contained already. And the compact model is also included, so you can simulate the whole PICs without knowing what's actually inside the black box. Once a circuit is done, the mask is generated. It's INT that's going to be replacing the black box, so neither the client can see our IP, and we will never have any idea of the mask design. In terms of views, it's quite well integrated inside Luceda. So this is a classic code of Luceda AppKeys, and you will just have to add the line to import the PDK of apply Nanotools, and under it you can call for our library on top of it with this second line, and the technology are compatible, etc. So there is going to be no issue. As you can see here, I can import the directional coupler from our library. So you would see this black box and, for example, the grating coupler here. Doing so, you can generate a mask. So this is a small example of a Mach-Zehnder interferometer, all routed within IPKeys with the grating couplers. If you want to go a bit further and use more extensively our IP library, you can even design a hybrid 90-degree here. So it's used for coherent communications in the C-band. So what I did here is we used our MMI 1x2, 3 MMI 2x2 that are very small, as you can see, compared to the conventional MMI 1x2. Some crossings, and we can route all of it up to the grating couplers. And this is the simulation that we obtain with the Café software inside IPKeys. The high performance and broadband aspect of our devices allow you to have, for example, here, a very low coupling mode rejection ratio of way below minus 20 dB. So this design is going to be present in the library. So as soon as you download it, you will be able to run it and to start to design from this and to inspire for your own PIC. Of course, this library is compatible with Canvas. So for designers who prefer to use a GUI-based design, you can see all our 9 components here and drag and drop them. And finally, we have more data. As I said, we are very focused into robustness of our device. So we always simulate corner. We do always Monte Carlo analysis. So I've just plotted them here, but if any client wants to have access to this to even make a more first time right device, we can always implement these simulations inside the new software of Luceda, which is called a circuit analyzer. So we would be able to do layout aware, corner, or Monte Carlo analysis. Thanks for your attention. If you want to have access to our IP, you have a link that Cameron showed directly on the platform, but you also access it through our platform and send us a mail directly to customers@alcyonphotonics.com and ask any doubts you have.
Okay, thank you very much to both Cameron and Thibaut. So we can now take questions. If anyone would like to ask a question in person, feel free to unmute yourself and ask. Otherwise, we'll go to questions from the chat. Does anybody have a question at this stage? If not, there was one question in the chat, and it was a question from Pierre, and it was about the possibility of tuning the splitting ratio. Is that possible, Thibaut?
Hi, Pierre. So yeah, it's possible at the directional coupler. We can adjust the number of periods and just make it longer or smaller to have a wide variety of coupling ratios.
Okay. And are there any other questions in the chat at this stage? Or anyone like to ask a question live? I don't see anything in the chat at this stage, so maybe I could ask a question to Cameron quickly. You mentioned the process of submitting a layout for fabrication. Maybe you could outline that a little bit.
Yeah, I'm glad you asked. So let me share my screen again here. So I'll try to do this as quickly as possible. So I just want to show everyone just how easy it is to submit something to us here. So we've got a script here that we can run through IPKIS, and we can generate ourselves a sort of directional coupler test circuit, we'll call it. So for IO, for IO, you can choose one as your input. You can measure, your splitting ratio from these two grating couplers here. So we'll work with this very simple GDS here, and we'll submit that to our fabrication service. So there's a submit a design form here where you can just give your design some kind of name, test directional coupler. I only want one of these. I want to join our May MPW run. I want it on 220 SOI. Yes, I want some oxide cladding on top because my grating couplers require that. But no, I don't have any heaters, no edge couplers, no dicing requirements, no SEMs either. Let's just keep it simple. When you create an account with us, all your billing stuff's in there already, so that's all sort of pre-filled and just gives us an idea of sort of how you plan on administering your order. If your design uses Alcyon black boxes, this part here is where you can put in a little code that they give you that just sort of helps us identify you and determines if you have a license to use the components. Right now I'm just using ours, so I'll just skip that for now. Once you create an order in our system, you can just go click the upload button here. We'll go find this GDS that we just created using Luceda. We'll attach it to our design. It's a really small file, so of course it uploads really fast. So this little checkbox says, hey, you've submitted it. This is running some checks on it to make sure that it's MPW compliant. This doesn't auto refresh yet, so you might have to just refresh this page. And once it's done the basic checks, you can actually go here and view a report. Gives you a little kind of DRC report. In this case, it didn't find any errors, so we're good. And you can even see a little thumbnail of your design. So we zoom in here. This should look familiar to us because that's exactly what we previewed in Luceda IPKIS. Of course, it's a very basic circuit, but imagine a full tape out here. And then the last step is really just to hit the submit button, verify that all your details are correct, and submit the order to us. It's as easy as that. Now, of course, if you have DRC errors, you're gonna maybe see some interesting information in here, and it'll give you the opportunity to download an error report file, and then you can work through those errors individually until you squash them all.
Great. Thanks, Cameron. There's another couple of questions that came up in the chat. One of them, Cameron, you already answered, but maybe I'll just read it out so people can hear it. So it was a question from Nirav where he asked, what is the writing field of the E-beam process? Yeah, and then maybe you could just quickly give the answer out loud.
Yeah, sure. So e-beam technology, as people may or may not know, uses right fields. So you're discretizing your entire PIC into these fields of a certain size. In this case, for our process, we choose a 500 micron block as our field size. The tool can go up to 1 millimeter fields, but we choose 500 just because it allows for the minimal amount of spatial distortions across the right field. So when we chop up your design into these 500 micron right fields, we also use the spatial averaging technique to overlap those fields across the boundaries so that you don't see any significant errors along those boundaries. Because as you can imagine, the tool has to be really good at stitching these fields together and making, say a waveguide that's crossing these two fields, they have to line up pretty well exactly. With the spatial averaging technique, we overlap the field boundaries so that any features that are sort of near the edge of the field will, during the first pass of the beam, we'll experience being on the edge of the field, and then in the second pass of the E-beam, that structure will actually be in the center of the second pass. I don't want to get too technical here, but it's a way to mitigate these stitch boundaries. And so we've also characterized losses, found that they're below the error margin of what we can measure across very long waveguides crossing several right fields across centimeters. So in essence, you don't have to worry about the fields with our process unless you're doing some very specialty stuff.
Okay, great. Thanks, Cameron. Nice. And so there's another question from Pierre. This is for Alcyon. So Thibaut, how does the license model work, and are the components licensed per use or per design? If you could elaborate on that.
Exactly, is we have a listing of the components. Like as soon as you tape out with ANT, we receive the list of the devices that have been used and how many in the mask, and the licensing is based on this. So per component.
Okay. Nice. Thank
Thanks
you
for
very
the
much.
questions.
I don't see any other questions in the chat at this stage, so we are coming to the end of time. So if it's the last chance to ask a few questions, you can unmute yourselves if you like. Just in the meantime, as you see on this slide, we have links to all of the companies here today. So please go and check these out. There's lots of really interesting material and things to learn, whether it's fabrication, about IP, about the design platform of Luceda, and all kinds of application examples you can access. So please go and check these out to learn more. And if you have any questions, you can reach out to all of us following contacts on these link pages. So please reach out if you don't have questions you want to ask now, but come up afterwards. Okay. As there are no further questions, I guess we can stop the session here. I'd like to thank everyone for attending and for asking questions. And yeah, please reach out to any of us if something comes up after the event. We'll happily talk to you and go into further details. Okay, thank you very much, everyone. We'll end the session there. Thanks. Goodbye.
Thanks.
Thanks.
Bye.
Goodbye.